Welcome to our review of linear equations. Before we get too far into a college algebra course, we should make sure, day one, that we are up to snuff on solving some basic equations. And by basic, I mean linear. And by linear, I mean you're going to have x's. You're not going to have x squareds. Nope, nope, nope. You're not going to have the square root of x. Nope, nope, nope. You're not going to have x in a denominator. Nope, nope, nope. You're going to have x terms. Just x terms. Those are what I mean by basic equations. The official word would be linear equations. So anyway, before I get to solving linear equations, there's basically three foundational principles or whatever that we need to make sure that we're perfect on. Hopefully you've seen all of these before and it's just a review, but it's worth a close look. So anyway, distributing. What's that? That's what you do when you remove parentheses. Now I want to do this actually the old way. Remember order of operations? There's an order of operations agreement that says when we go mixing up lots of math symbols, we should use them in a certain order. There's the old please excuse my dear Aunt Sally. And what it says is if there's any parentheses, finish what's in the parentheses. Well, notice that works here, right? 12 minus 5. I can do that. I can finish that. So if I go 12 minus 5, I get a 7. So what we've really got is a 2 times a 7, right? So remember, a number up against a parentheses, it implies that you're multiplying. So anyway, 2 times 7, you get 14. Woohoo! So that was cool. That's doing it the old way. That's not called distributing, by the way. That was just evaluating the darn thing, saying, what's this equal? Now, distributing is the thing I need to show you here, and it goes like this. You see that too, how it's multiplying both of these things? The 12 minus 5 is kind of grouped into a parentheses. That's what I mean by both of these things. The 2 is multiplying the group, might be a better way to say it. And in order for the 2 to multiply that group, you basically got to multiply the 2 by everything in the group. So 2 times 12 gives you a 24, and then 2 times negative 5 gives you a minus 10. So you can think of that as 24 minus 10. But look at this, 24 minus 10, guess what? That's 14. Yep. So that just proves to you that this distributing idea works just splendid. It works fine. Now sometimes you're not going to have two choices, like I could distribute, or I don't have to distribute. I could just go 12 minus 5 first, right? But like in a situation like this one where you've got an x in there, how are you supposed to finish doing x minus 3 if you don't know what x is? If you don't know what x is, then you really can't do x minus 3 first. And so this is a situation where really the only way to get rid of the parentheses is to distribute. That's your only choice. And so you'd go 2 times x this way, and then minus the 2 times 3 is 6. And you'd get 2x minus 6. Okay? So that's the whole idea of distributing. So we got more examples though. What I'm trying to say with this one, and by the way, you could do this one the old way because it's just numbers. 5 plus 2 is 7, right? So what we would have here is we'd have a negative 3 multiplying a 7, and so that's going to be a negative 21, okay? So I do it that way just so we can be absolutely sure. Look, the answer is supposed to be negative 21. Let's make sure that that's what we get when we distribute. So distribute. Negative 3 times 5 is a negative 15, and what's important here, make sure you multiply the negative 3 times the 2 to get a negative 6. Okay, so the sign goes with you is what I'm trying to point out here. So you get a negative 3. Okay, negative 3 times 5, negative 15. Negative 3 times 2 is negative 6. Now you can add the negative 15, the negative 6, and guess what? We really do get the negative 21. So when you're doing equations where you have like an x in here, again, you don't have the choice of let me just combine what's in the parentheses first. You can't combine what's in. They're not like terms. You can't add an x and a 2 because an x is one thing and a 2 is a pure number. So you just have to distribute. So negative 3 times the x, and then again, negative goes with you. Negative 3 times 2 is a negative 6. Okay. Hope you're digging on this distributing thing. Now, this one, let's do this because I can. 7 minus 10 is a negative 3, right? So I got a negative 3 in there. I've got a negative out front, and then I've got a negative 3 in my parentheses. Now this is a negative, go away. Oh, I never know what's going on. Okay, go away. It went away. So I have a negative negative, which is a positive, right? A double negative is a positive. So you're supposed to get a positive 3 when you do this. Now, will I get that if I distribute? I will if I'm careful. So what I was saying before, the negative goes with you. So negative 7 and then negative times negative makes a positive 10. And then notice negative 7 plus 10 really is a positive 3. It's working. Now, if you want, some people are more comfortable, instead of just thinking this as a negative 7 minus 10 like this, just you can kind of stick a 1 in there for free, because that really is the same thing. Negative 1 times 7, which is negative 7. Negative 1 times negative 10, which is positive 10. And you end up at the positive 3. So if you like to put the 1 there, go ahead. 1s are kind of cheap. As for this one, just remember, when you see this kind of thing, you're playing with some big long equation or something, you're playing with this kind of thing, in order to get rid of those parentheses, you want to distribute what basically amounts to a negative 1 in front, but the negative 1 times x makes a negative x, and again, make sure you get this. Negative times negative is positive 2. Okay. So distributing, that's one of the things we're going to need when we're playing with equations. And what do we need it for? We need it when we have parentheses in our equation. We can get rid of the parentheses by distributing. Foundational principle number 2. Remember, there's 3 of them. Number 2, combining like terms. So like terms can be added. If they're not like terms, they cannot. Okay, combine like terms, do not combine unlike terms. So what do I mean by like terms? See, these are like terms. Why? Because they're both x's. They're both counting the same thing. Hey, I got 2 x's and 5 x's. Well, guess what? That's 7 x's. They're both x terms, so they can be added together. Just like you can add 2 apples, you can add 2 oranges. You add them together. 2 x's and 5 x's make 7 x's. Here, these are both pure numbers. Just pure numbers. 12s minus 17. Well, they're both pure numbers. Go ahead and combine them. 12 take away 17 is a negative 5. Over here, 3x plus 2. That is not 5 of anythings. Those are not like terms. Leave it alone. It's done. That's counting x's, but that's a pure number. That's not really counting anything, I guess. It's a pure number. 3x and 2 are not like terms. They do not get added together. Just leave it like that. 3x plus 2. You're done. You're done. Now, this one's getting a little bit funkier because we got 3 terms here. So what you got to do is you got to look at terms that are the same, or at least like. If this has an x and this has an x, then those are called like terms. They're both x terms. To be like terms, you have to either be both pure numbers or you both have x. Or later on, if they both have x squared, those would be like terms and so on. But anyway, negative 3x plus 4x. So I can add those together. You take the sign in front like it's a tag. You think of this as a negative 3x and a positive 4x. And then you add a negative 3x and a positive 4x. You get a positive 1x. That's x. And then the 8 is just kicking around. Schlep it along. X plus 8. Done. Okay, and then the last example, this one. I like this one because it's a situation you'll face every now and then. You want to be ready for it. First of all, there's lots of terms, so you got to make sure you put like terms together and you don't put unlike terms together, right? But the main challenge, of course, is look at all this. I'm going to add a positive. I'm going to subtract a positive. I'm going to add a negative. I'm going to subtract a negative. Oh my gosh. My head spins when I try to do too much of that stuff. So I'm going to show you how I handle this. I handle this by saying, hey, you know what? This is like a plus 1 times a plus 4. That's a plus 4. That's all it is. So I've got my negative 12x here, and then just say it's plus 4. This is like a minus 1 times a positive 5, so that's a minus 5. Just take these two signs, in other words. Let's get the 1's out of there. Just take this negative times positive is negative. Get it? Positive times positive is positive. Get it? That's kind of the shortcut you can do. Of course, you can think of it as it's a negative 1 times a positive, whatever. But right here, I'm just going to say, well, this is a positive times a negative is a negative. And this is a negative times a negative is a positive. 7x. Okay, cool. So I undoubled my signs, so to speak. No more doubled up signs. Now, this, I think, is a little easier to deal with. You take all your x terms, and remember the sign in front is like a tag that's attached to it. So that's a negative 12x, and that's a positive 7x, and those are my only two x terms. So you put those together, negative 12 plus 7 is negative 5x. And then all of these are pure numbers. They can go together. 4, take away 5, take away 6 more is what, negative 7 or something? Sure, negative 7. And so that all becomes just a nice little negative 5x minus 7. Okay, cool. So we can combine our like terms and our not combine our not like terms. We can distribute to remove parentheses. What else do we need? We need one more little tool, one more little foundational piece. And I'm calling it Teeter-Totter Theory. Now let me show you why I'm calling it Teeter-Totter Theory. Let's get green here. This is an equation. This is supposed to be the same as this. X plus 5 is supposed to be the same as 8. That would mean that if you made a scale here, see, like a balance. So that's supposed to be like a balance. If you put an x plus 5 on this side, and you put an 8 on this side, it should be balanced. They should actually balance quite nicely. Now I'm going to use a pictograph kind of a thing here. The x is like this mysterious box that I don't know what it weighs, and that's what I would really like to know, is what does that weigh? And then the 5 is like saying I've got 5 more like pound weights or something. On the other side I have 8 pound weights. Okay, so I've got x over here with 5 loose pound weights, and over here I got 8 pound weights. Okay, now just looking at this picture, can you kind of tell what must be in the x box? How many weights, how many pound weights are in the x box? Well, you might be able to see it, and if you don't see it, that's fine, because what I'll do is I'll show you. First, the problem is when you weigh something, you don't want this stuff over here. You just want the x box. You want to weigh the x box? You just put the x box there. Get rid of those. Get rid of them. Take them right off. Now, of course, if you take them off the left side, the scale's going to go out of balance unless you take an equal number off the right side. So you take those off. So I took 5 off the left, I took 5 off the right, and you can see that what's left here is x and what's left here is 3. And that's our solution. That's what I call Teeter-Totter Theory. We're trying to get the x box on one side of the teeter-totter, and you got to do the, if you take 5 off of one side, you got to take 5 off the other side. The old what you do to one side, you do to the other side trick. So usually the way people do this is instead of drawing teeter-totters, I'll just move my teeter-totter down a little bit. Instead of drawing teeter-totters, they'll just do the old, hey, I'm going to subtract 5 on both sides of my equation. See? So over here, the plus 5 minus 5 cancels, and over here, the 8 minus 5 is a 3. Well, what you do to one side, you do to the other. That's the Teeter-Totter Theory. I do like taking close looks at these things like this. 2x equals 8. How would I draw that as a teeter-totter? Or a balance scale, or whatever you want to call it. Well, the right side has 8 pound weights again. The left side has 2 x boxes. What's that look like? Well, that's kind of like saying you get, 2 x boxes. Like that. So you got 2 x boxes equals the 8 loose pound weights on the other side. Now, notice that subtracting on both sides doesn't quite work, right? You can say, oh, I'm going to subtract x. But the problem is you don't know how many pound weights are in an x box. You don't know. You don't know what number to subtract, in other words. So you take another thing. You do the John Belushi Samurai Delicatessen, and you go, whoop, and you cut it in half. Cut that side in half and throw that out. Now, that'll work as long as you also cut the other side in half. Whoop, cut it in half and throw half out. Get it? So now you can see that I only have 1 x box, and over here I got 4 loose pound weights. X is 4. So it's the old, not subtract on both sides, but we actually, by cut in half, you could say we divided both sides by 2. Move. Okay. So how does that look like if we don't go fancy drawing stuff? Again, you look at this and you say subtracting 2 is not the thing here. For one thing, 2x and 2 are not like terms. You can't subtract a 2x minus 2. They're not like terms. They don't combine in any way, or whatever. What you have to do here in this situation, that actually says 2 times x, right? When you put a 2 right up to an x. So in order to undo the times x, what you need to do is you need to divide on both sides. Or what I'm thinking of is I'm cutting it in half. I'm canceling the 2's. But the way you're canceling the 2's is you're basically dividing both sides by 2, which means cut in half. And so you divide both sides by 2. The left side has just an x now. The right side is 8 over 2, which is 4, which is what we were expecting. Cool. Now, to make a long story short, looking at this one, notice we got 2 actions we're going to have to perform here, because at some point we're going to be needing to divide by 2 so that that's just an x, and at some point we're going to want to subtract the 6 on both sides to get rid of that. So I'm just going to say outright, here I go, subtract, or I won't even say it that way. I'm going to say save the divide for last. It's safer that way. Save the divide for last. In other words, first I'm going to subtract 6 on both sides. So 2x equals 8 minus 6. So I basically subtracted 6 here and I subtracted 6 here. So that means that 2x, 8 minus 6 is 2. Okay. Now is the part where I will cancel the 2 on both sides. Divide both sides by 2. 2 over 2 is 1. So apparently the solution is just x equals 1. X equals 1. You can check your solution by putting it in here. If I said 2 times 1, that would be 2. Plus 6, that really is 8. So yes, that solution really does work. Okay? You can always check your answers like that. Just plug it right back in, make sure it works. It's the fastest way in the world to make sure you're getting the problem right. That's really good advice on a test. Just plug it in, make sure it works. Maybe before I leave this one behind, I'll just kind of show you what goes wrong, or what can go wrong anyway, if you were to say, oh, I'm going to divide by 2 first. I'll divide by 2. So the 2's cancel. 8 divided by 2 is 4. Okay, now you'll subtract 6, right? So now you've got x, 4, you get negative 2, 4 minus 6, negative 2. But you're not supposed to get negative 2, you're supposed to get 1, remember? So it's the wrong answer. Well, that ought to be a sign that something's screwy, right? Something's screwy here. And so you might be saying, well, why can't I divide by 2? I'm doing the same thing to both sides. And the thing is, you're not doing the same thing to both sides. You're actually not. Because, get this out of the way, when you divided by 2, you took the right side and divided it by 2. Yep, you did. But the left side, you didn't divide the left side by 2. You just picked one of the terms and divide it by 2. If you want to divide the left side by 2, you would have to divide all of them, by 2. Now, this will work. So the 2's cancel here, and it's an x. The 6 over 2 makes a 3. The 8 over 2 makes a 4. And notice that when you subtract 3 on both sides, you do get the right answer of 1. Okay? So I guess the moral of the story is if you want to divide first, you can. Just make sure that if you divide first, you're dividing all of your terms by 2. Or if you're dividing by 2, divide all of your terms, not just a couple of them. Just you can't just say, well, these are the terms I don't like, I'll divide those by 2. No, it doesn't work that way. If you're going to divide both sides by 2, then you divide everything on each side by 2, everything, and then it'll work. Or if you want to just keep it easy, just do what we were saying before and save the dividing for last, and you'll never have a problem. Okay, so those are our foundational principles. Now, let's solve some equations. Now, there's a 4-step plan of attack that we can use to solve all basic linear equations. What is this plan of attack? Step 1 is going to be get rid of parentheses, distribute. So if you have any parentheses, get rid of them. Let's look at this example here right now. Let's do this one right now. 7x plus 4 equals 12x minus 1. Do I see any parentheses? No, I don't. Good. Step 1 is done already. In fact, let me kind of go like this. Step 1 is done. Step 2, on each side, combine like terms together. On each side. In other words, I'm looking at the left side. Can I combine a 7x and a 4? No, they're not like terms. One's an x term, one's a pure number. How about on the right side? Again, one's an x term, one's a pure number. There is no combining. Now, on each side is very important, because what you do not want to do is you don't want to be thinking in terms of combining the 7x and the 12x. Okay, you can't. They're not on the same side of the equation. You don't want to be thinking of combining the 4 and the negative 1, because, again, they're separated by the equals. The equals is like a dividing line. You don't combine things that are on different sides of the field, so to speak. So actually, step 2, there's nothing to do there either. So I guess you'd say it's done. Okay, now do the add-subtract teeter-totter repeatedly. Okay, so, and it says what? Until you're left with a single x term on one side and a single number term on the other. Okay, so what I'm going to do, I like having my x here on the left. I like that. But see that 4? We don't want that 4. So I'm gonna subtract 4 on both sides right now. So I've got a 7x here, I've got a 12x here. The minus 1 and the minus 4 makes a minus 5. Okay, cool. The thing is, it's nice to have just an x term here, but it would be nicer if I had just a number over here. I don't want that 12x there. No, I don't. So now I'm going to subtract 12x on both sides. So 7x take away 12x is a negative 5x, and over here I've got a negative 5. Okay. So that's what it was saying here when it said until you're left with a single x term on one side, yep, just one x term, and a single number term on the other, yep, just a single number term. That's what all that stuff is saying. Okay, finally we get to step 4. Last step, always save the dividing by last. That's my tip. Always save the dividing by last. Now in this case, what I want to divide by is not just a 5, but I want to divide the negative off too. Right? I want everything to cancel here, so that's just an x. And a negative divided by a negative is a positive, and a 5 divided by a 5 is a 1. Oh my gosh, we got x equals 1 again. Okay. So I put this problem's here only because I usually get a question in class. I show them my way to solve the problem, and then someone says, well, wait a minute, couldn't you just? And it's like, I prove, yeah, you could just. Could just what? Well, you could just if you wanted to. You don't have to put x on the left. You could put x on the right. In other words, cancel the x's from the left. I got 4 equals 12 minus 7 is a 5x, and then don't forget your minus 1. Why would you want x on the right instead of on the left? The only reason is because now it's a positive 5x. And it's just, if you got a negative, if negatives make you, anxious or whatever, you might want to make the 5x, put the x's on the right so they're positive. But it doesn't matter. I just always put my x's on the left. I'm okay with negatives. They don't bother me so much. So to continue this one, if you're trying to get x by itself over here, then you'd say, well, I don't want the minus 1, so add 1 on both sides. 4 plus 1 makes a 5, equals a 5x. This is the part where you're saying, I don't want 5x, I just want x. So I divide both sides by 5, and 5 over 5. Of course, you get the same answer. You have to get the same answer. As long as you do legal steps every time, then it doesn't particularly matter if you do exactly the same sequence as I do. You can follow your own path in this world. That's what makes math exciting to me, is that you can take all kinds of different approaches and always end up at the same answer at the end. It's like the answer is always waiting for you at the end, but you just have to make sure that every step is a correct step. So, do I need my x on the left? No. I just need my x alone is the main point. All right, let's see. What do we got here? Oh, wait a minute. I think I'm remembering something. Oh, yeah, I am remembering something. This problem, you're going to want to put a flag next to it. This problem actually got some important information in it. But first, let's just do what we've been doing and follow our steps, the 4-step plan up here. So let me bring back up so we can see it again. Start over. Okay. First thing we should do, distribute to get rid of parentheses. Okay, if I got any, I don't have any parentheses. On each side, combine like terms. Okay. So on the left side, notice the 8 and the 2 go together. That's a 10. And then that's a minus 3x. On the right side, notice a 2x take away 5x is a negative 3x. And then I've got my plus 11. Okay, so that's the old combine things on both sides trick. Now what I'm going to do is I want my x, let's say I want my x on the left side, so I'm going to do the old add the 3x, so it cancels over here, and I'll add the 3x over here as well. And when I do that, the left side is a 10. Minus 3x plus 3x. Well, that's 0x. And 0x is just not there. It's 0. It's not there. On the right, negative 3x plus 3x is, again, that's 0x. And 0x means it's not there because it's 0 times x. So it's not there. Equals 11. So the question is, where's x? Where did x go? My equation doesn't have an x in it anymore. Come on. I'm supposed to have an x. And it's like, well, you won't always have an x. That's the whole problem. So here, let's get out the red ink, right? First question, does 10 equal 11? And the answer is never. 10 never equals 11, which means the equation is never solved. That's what this means. In other words, there's no value of x that will make this equation work. There is nothing you could plug in for x, here, 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 and here. There's nothing you could plug in that would ever work. That's what it means when you get this 10 equals 11 stuff. This is, by the way, if you want a nice official name for it, it's called a contradiction. The left side equals the right side. No, it cannot. You're contradicting yourself. That's like saying green equals red. It cannot be. It cannot be. You're contradicting. It's a contradiction. No. 10 equals 11. No, it doesn't ever. So if the x goes away, you got 0x here. If the x goes away, it does. You just have to accept it. Oh, my x went away. It's gone. But then you look at what's left here, 10 equals 11. And you say, well, that's no good. 10 equals 11 is impossible. This equation is impossible. It's impossible to solve the equation. There is no solution. Now, PS, maybe a slightly different color for a PS. And this is part of our flag here. Wow, that's a weird looking PS. PS. Okay. Let's say you had something like, I don't know, let's just make up this equation. 3x plus 5 equals 3x plus 5. Okay. If I subtract 3x on both sides, because I'm trying to get the x off the right, now what have I got? I've got 5 equals 5. Right, because the 3x's are canceling to 0. The 3x's are canceling to 0. The left side's a 5, the right side's a 5. 5 equals 5. That's not the same situation as over here. We're not going to say, oh, x went away, no solution, because the reason we said no solution is x went away and it said something impossible. 10 equals 11. This is not impossible. This is guaranteed. This is always true. The official word is tautology. Might as well write that down because you might hear me say it now and then. Tautology. A tautology is just when you say green equals green. It's 5 equals 5. It's a tautology. Of course it's true. It's automatically satisfied. Let's put it that way. 5 is always equal to 5. Automatically satisfied. So what does that mean? That means that this equation is automatically satisfied, and it doesn't matter what you plug in for x. If I plug in 1 for x, right, I'd have a 3 plus a 5 is an 8. 3 times 1, I'd have a 3 plus a 5 is an 8, of course. If I plugged in x equals 2, 3 times 2, I'd have a 6 plus a 5 is an 11. I'd have a 6 plus it's going to be the same no matter what. Automatically satisfied. What we say is all real numbers are solutions. X can be anything. Any real number will make the equation work. So there's 2 special cases to be aware of. There's the old x went away and I'm left with a contradiction, something impossible, 10 equals 11, in which case you say no solution. Or x goes away and you end up with a tautology, something that's automatically true, that's always true, in which case you say all real numbers. Okay, so we flagged it because those are 2 important special cases to be aware of. Okay. Getting back to our main mission, which was to use this 4-step plan to solve equations. Here's one where we can use the 4-step plan. Remember, step 1 is to get rid of any parentheses, and this time we do have parentheses, so I'm going to be distributing 4 times 2x, 4 times negative 3, so that's an 8x minus a 12. Over here I got a 20, And remember, this is kind of like having a minus 1 in front. This negative distributes as well. I got a negative x and a negative 1, right? Because a negative 1 times a 1 is a negative 1. So that's the get rid of parentheses step. If I look at the left side, I say I don't have any like terms. If I look at the right side, I say I do have two like terms. The 20 minus 1 is a 19 minus x. Now, I want to maybe add x on both sides, and maybe I'll use a different color to do that. I'm going to add x. I'm going to add x. And so I've got a 9x minus 12 equals just a 19. Okay. Now what? Let's add 12 on both sides. Add 12. Add 12. So I got 9x is equal to 19, 29, 31. Okay, cool. And the last step is to divide both sides by the 9. So it's a 31 on top, it's a 9 on the bottom. And in this class, improper fractions are just happy. Improper fractions are happy. I mean reduced. But, you know, what goes into 9? Basically a 3. Does 3 go into 31? No, this won't reduce. So improper fractions are fine. Mixed numbers are like, nah. Nah. So you could call that 3 4/9, but just don't. This is the preferred style. In a college algebra setting, this is our preferred style. A nice, reduced, improper fraction. Okay. So those are the 4 steps you can use for any linear equation. Again, that just means x is to the 1 power. The one thing we got to do, though, is got to make sure that we can handle our fractions fine. So I think I've got, how many fraction examples have I got? 1, 2, 3, 4. I got 4 fraction examples. Okay. It tends to be a weak spot these days, let's put it that way. So it's definitely worth a look. So we get to remember, you know, what do you do to add fractions? What do you do to multiply fractions? All that good stuff. So this first one. Well, we're supposed to get rid of parentheses first, right? So that means I'm distributing the 3 times the 3/5 and the 3 times the negative 2/3. Now, when you multiply 3 times 3/5, what do you get? You get 9/5. Sometimes people want to make that a 9/15, but you don't multiply the bottom by 5. Think of the 3 as like 3 over 1. Any whole number, you can put a 1 underneath. And so when you're multiplying a 3 over 1 times a 3 over 5, multiplying it straight across, you get a 9/5. Okay, so the 3 times the 3/5 x is a 9/5, and I should really put the x there. 9/5 x. Okay, let's get rid of that. It's bothering me. Okay. Now, we got to also do this. 3 times the negative 2/3. Now, after a while, you'll learn to see this. That's just a 2. Okay. Again, that 3 in front is like a 3 over 1. And it's multiplying the negative 2/3. And here's the thing. You could, I guess, multiply straight across and get a negative 6 over 3. But negative 6 over 3 reduces to just a negative 2. What I'd prefer, you notice, is that, see, when you're multiplying fractions, you can do this thing called cross-canceling. Only when multiplying fractions. But when you are multiplying fractions, it's a good idea to look for cross-canceling. Keep your numbers small. You're a lot less likely to make any mistake. Plus, it makes the rest of the problem easier. So anyway, those 3's are canceling. So when I multiply straight across, I have 1 times a negative 2 is a negative 2. I have 1 times a 1 is a 1. And it really is just a negative 2. Okay, the 3's cancel. It's just a negative 2. Okay, now that's bothering me. Let's get rid of all this stuff. Get rid of it. So that's the left side. And now what's on the right side? Well, it is a negative 1/4, I guess. Okay, so what should we do now? Well, I've got my x on the left. That's cool. I guess I want to add 2 on both sides. That'll cancel the plus 2's. Now, how do you add a negative 1/4 plus a 2? Well, first of all, that's a 9/5 x. Okay, you got to remember this. when you're adding or subtracting fractions, you got to do the common denominator thing. So again, a whole number is like over 1. 2 is like 2 over 1. My common denominator here would be 4. So in order to make the 2 over 1 into something over 4, I have to basically multiply by 1. Multiply the top and bottom by 4. And when you do that, you get, let's see, I got a negative 1/4 plus 2 times 4 is 8 on the top. 1 times 4 is 4 on the bottom. Okay, let's bring this problem over here now. I got a 9/5 x on the left side and on the right side. See, now that everybody's fourths, I can just kind of add across the top here. Negative 1 plus 8 is 7/4. So when you're adding fractions, make sure you get a common denominator. The 4 is almost like saying I got negative 1/4 plus 8/4 gives me 7/4. It's almost like a like terms thing now, right? Except instead of x's, it's quarters. So negative 1/4 plus 8/4. I got 7/4. Cool. Lastly, we got to get rid of that 9/5 on the x. Boy, is that hideous looking, right? Now, I'm going to write this down just because I see a lot of other people write this down. But as soon as I write this down, I'm going to say, ooh, hideous, hideous, hideous. There's a trick you can do. Instead of dividing, multiply by the reciprocal. Get it? You multiply by the reciprocal. Because the whole idea is basically we want the 9/5 to cancel away. Well, if you multiply by 5/9, cross-canceling, the 9s will cancel, the 5s will cancel. That's what I was saying over here, remember, is that when you're multiplying fractions, you should cross-cancel first. So I set myself up to cross-cancel a bunch of stuff. And so the 5s cancel, the 9s cancel. It's an x. And then over here, well, I can't cancel 7 into 9. I can't cancel 4 into 5. So I guess I just go straight across. 7 times 5 is a 35 on top. 4 times 9 is a 36 on the bottom. The answer is 35 over 36. Cool. So that was handling fractions kind of the brute force way. Maybe I'll write that down. And by brute force, I mean I used my rules for multiplying fractions. I used my rules for adding fractions and so on. This one, I want to show you a trick. And if you're careful, this trick will save you lots of, well, it can at least save you lots of time. So I could, I suppose, say here's my x term. I'm going to subtract 3/4 on both sides. And then I'm going to have to figure out how to deal with the 2/3. Or you can do something called clearing the fractions. Make all change. Maybe I should say change. Change them all. Change all terms to have a common denominator. Remember LCD, that least common denominator. When you look at a 4 and a 3 and a 2. The least common denominator there of 12 is 12, because 4 and 3 both go into 12, 2 goes into 12, yep, 12. So what I'm going to do is I'm going to make everything be 12ths. Now this one I'm going to have to multiply by 3 over 3 to get 9 over 12. This one I'm going to have to multiply by 4 over 4 to get 8 over 12x. And then this one I'm going to have to multiply by 6 over 6. Get 6/12. Okay, so everybody's 12ths. Now here's the cool part. If everybody's 12ths, then the 12ths don't matter anymore. Get it? It's all 12ths. Well, cancel the 12s. I suppose you could say I'm multiplying both sides of my equation by 12. And when I multiply the left side by 12, those 12s cancel, those 12s cancel, and then the right, those, okay, boom. It's all the same denominator, so it goes away. And then you're practically done. Look at this. Subtract 9 on both sides. Divide both sides by 8. What could be happier? So you end up with a fraction answer, all right. But I think it was easier to just clear the fractions first. So this next example, I want to look at this and I want to say, okay, notice I put the problem there twice. Let's do it the brute force way, and let's do it the clear the fractions way. We'll do it each way, something like that. If I were to do this brute force, I would have to multiply 2/5 times 1. Okay, that's not so bad. Anything times 1 is itself. I'd have to multiply 2/5 by 3/2. I hope you can see those 2's are canceling, leaving me with a 3/5 times an x equals a 1/3. From here, what should I do? Well, I can leave the 3/5 x alone, but I should be subtracting that 2/5 on both sides, right? Now to do this, I need a common denominator type thing. My common denominator would be 15ths. So times 5 times 5, I got a 5/15. Times 3 times 3, I got a 6/15. So 3/5 x equals, I subtract the 5 minus the 6, I get a negative 1/15. Okay, almost there, folks. Now, I don't want the 3/5 there. I could divide by 3/5, but it's easier if I multiply by the reciprocal. So the 3's cancel, the 5's cancel, it's x. Over here, make sure you do the cross canceling. It makes your life so much easier. 5 cancels into 15 3 times. And so what we're left with is a negative 1 times 1. Oops. Let's get the right color here. And first of all, it's negative. 1 times 1 is 1. 3 times 3 is 9. You're supposed to get negative 1/9. That actually wasn't so bad doing it the brute force way. But if you wanted to do it by clearing fractions, you could. But the thing I have to emphasize here, if you want to make a common denominator of, let's see, I'm looking at the 5, I'm looking at the 3, 15ths, right? Notice I'm looking at the 5. I'm not looking inside the parentheses. You don't look inside the parentheses. You look outside the parentheses. And it's because this is all one term, the way it's written right now. It's 2/5 times stuff. It's all one term. So you can't be like multiplying this by something, this by something, this, but you can't be multiplying all these different pieces by something. So if you want to make 15ths, that's fine. Make this into 15ths, so that would be times what, 3/3? 6/15ths, and then leave this alone. And then times 5 times 5, that would be a 5/15ths. Now you can cancel the 15ths. This is the part where you can cancel the 15ths. I'm canceling it from this whole left side is one term. You have to look at this as one term. Multiplication glues things together into a single term. So that's one term. And so anyway, the 15ths are canceling. But now look what I got here. I got this, I got to distribute here. 6 times 1 is 6. Now here's the good news. Whoa, what'd you do? Don't do that. Okay. A little bit wider. Okay, whatever. When you multiply 6 times 3/2, can you see what's going on there? 6/1 times 3/2. The 2 cancels into the 6 3 times, and you get a 9x. The right side is a 5. So 9x equals 5x. 5 take away 6 is -1. Divide both sides by 9, and we got the same answer. That's good. That's very, very good. You always want to get the same answer. Okay, one more nice, big, juicy example. Wow, do I really want to do this one twice? I don't know if I want to do this one twice. Let's see. Sometimes I use the clear the fractions trick sort of back and forth with the brute forces. In other words, let's say I wanted to, let's say I wanted to try to clear fractions, right? I see a 5. Now remember, this is all one term right now, so I'm just looking at the 5. I got a 3. Okay, I should make a common denominator of 15. Well, if I want to do it that way, this will be times 3 times 3. This is 6/15ths. And then this will be what it is, 1 plus 3/2 x minus. Now you got to do all the terms, right? This is all one term. That's why I didn't change what's in the parentheses. But this is another term now. Pluses and minuses separate the terms here. So a minus, I really have to write that as a 15/15x. This I'm going to make a times 5 times 5, so that's a 5/15 minus. And this kind of has a 1 in front, which I should make into a 15/15ths. Okay, I'm going to move this to the left a little bit so I don't get too crowded around here. Okay. So the 15ths can now cancel. Let's do that. From that term, from that term, from that term, from that term. And so what am I left with now? I'm left with, I got a 6 multiplying a 1 plus a 3/2 x. This is minus 15x equals 5. And this is minus 15 times a 2x plus 1. Okay, let's distribute. 6 plus, and when you multiply here, the 2 will cancel into the 6 3 times. You've got a 9x. Minus 15x equals 5. Distribute again. Minus 30x and minus 15. I got a 6. And then this is a minus 6x. Right? These make a minus 6x. 5 minus 15 is a negative 10 minus a 30x. Okay? Add 30x to both sides, which will cancel this one. So I got 6 plus 24x equals a negative 10. Okay, subtract 6 on both sides, which will get rid of this. 24x equals negative 16. And finally, divide both sides by 24. 16 over 24. And always look to reduce. I can cancel 8s. Cancel 8s. This is a 2/3. Woo! We got a negative 2/3. Now, like I was saying before, you should be able to do different sequence of steps, but as long as every step is legal, you should always get to the same answer at the end. So I'm going to do this a different way. I don't think that would have been my choice to make everything 15ths, because I don't know, it makes me nervous. I think what I would do is I would just go ahead and do brute force. 2/5 times 1 really is 2/5. Okay. 2/5 times 3/2. Again, the 2's are canceling here on the diagonal. So I'd have a 3/5 x. Then I'd have a minus x. Over here, a 1/3. Make sure you distribute the negative to both of these. Minus a 2x minus a 1. Now, on this side, I have two like terms. So it's going to be 2/5. Now, this is like having a 3/5 x minus, now this is like a 1 over 1. So I can multiply the top and bottom by 5 and call it a minus 5/5 x. Over here, I got 1/3, and taking away 1, I can call that a 3 over 3. Multiply top and bottom by 3, and then don't forget my minus 2x. So now I can combine these things. 2/5. 3/5 minus 5/5 is a minus 2/5 x. Over here, I got 1/3 minus 3/3 is a minus 2/3. Minus 2x. Okay. I guess I'm going to add 2x on both sides to get rid of that one. And maybe at the same time I'll subtract 2/5 on both sides to get rid of that. So my left side is a negative 2/5 x plus a 2 over 1 x. My right side is a negative 2/3 minus a 2/5. Okay, on the left side, I'm going to change colors now. On the left side, I should make a common denominator of 5. So multiply top and bottom by 5, and I'll have a 10 over 5x. Over here, I should make a common denominator of 15. So times 5 and 5, that's a negative 10/15. Times 3 over 3, this is a 6/15. Now I can combine my stuff because the denominators are the same. On the left side, negative 2 plus 10 is an 8/5 x. And over here, negative 10 minus 16 is a negative 16/15. Cool. Almost there. What we need to do now is get that 8/5 off the x. Again, you could divide by 8/5, but that looks gross. And besides, if the way to divide by a fraction anyway, if you want to divide by 8/5, what you end up doing is you end up multiplying by the reciprocal. So why don't we just do that right from the get-go? Multiply both sides by the reciprocal. 5's are canceling. 8's are canceling. It's an x. Over here, okay, cross-cancel time. Come back here. Okay, the 5 cancels into the 15 3 times. Okay, the 8 cancels into the 16 2 times. So what have I got? I got a negative. Top is 2 times 1. The bottom is 3 times 1. And boy, am I happy I got the same answer, because that would have been a bummer if I didn't. And I think that's the end. Okay, so this is all kinds of ways to handle fractions. In the end, it's largely a matter of taste. You know, which steps you do first, which steps you do second, and whether you're going to make everything have a common denominator right away or brute force it kind of like I was doing it. It's kind of all your choice. Anyway, just make sure you're nice and comfortable with all this stuff, that you can solve linear equations, basic linear equations. You can do the distributing and all that stuff, the like terms and all that stuff. You can get the x by itself. You can handle the fractions, and then you'll be off to a good start. Okay.